So first I shall discuss the discovery of the two-dimensional materials and different classes of two-dimensional materials I am going to discuss. And out of it, I shall mainly focus on the unique properties of the graphene, which is the most known as well as the mostly used material, two-dimensional materials. And I shall discuss some of the electronic structure of graphene and graphene analogous materials and how to synthesize these kind of 2D materials and its applications. So let me start from the three-dimensional materials because we are more familiar with the three-dimensional materials, a material where atoms are organized in a three-dimensional manner, in a periodic manner. And this is very known to us. And all the materials we generally see around us, all are three-dimensional materials. But however, a question remains, is it possible to develop a material which is two-dimensional materials? By the name two-dimensional material, I would like to refer a material where atoms are arranged in a plane. It's a two-dimensional plane. So for a long time, it had been known that it is impossible to get such kind of two-dimensional materials because of the fact that these kind of two-dimensional materials, to stabilize the total energy, it can, try to make the as smaller size as possible, and it will turn up to the some other shapes. It will not remain in the as a two-dimensional materials. So this was the challenge, and people thought that it is completely impossible to have the two-dimensional materials. And then when people think about the structure of the graphite, practically the graphite contains some layers, these kind of two-dimensional layers of carbon. As you can see from there, so if you see the structure of the graphite, which is generally used in pencil, actually it contains some layers of carbons, two-dimensional layers of carbon, and individual layers, they're connected by the van der Waals interaction. So these interactions are very poor, so that if you use this, if you draw something over the paper with the pencil, some tens of or hundreds of some layers comes on the sheet, which we generally see as some kind of line over there. Now, the people thought that is it possible to separate a single layer, not tens of layers or hundreds of layers? So then these two guys, Novoslav and this Andrew, they did a very simple experiment to separate the single layers of carbon, which are known as the graphene, because it is derived from the graphite, by a simple scotch taping method. They use a scotch tape and put some graphite powder over there, and they did the repeated taping and detaping over there. So few layers of graphite, few layer of graphene coming on the first taping, and then it's coming in the second step. Again, few layers come. By this process, statistically it may possible that they can get a single layer of graphite known as the graphene. And there was a parallel study done by Philip Kim. He studied in a different approach. He took some graphite column and knocked down one layer by another by the atomic force microscopic tip. But these two guys, whenever they separated it, then the question is how to check or how to confirm that these are the single layers. Fortunately, they have transferred all those layers, which is over the silicon dioxide coated silicon. The bottom layer is the silicon dioxide coated silicon, and this is commonly available in the lab. So they took that, and fortunately, this particular substrate was the best substrate for the transfer and to visualize it. So over there, you can see that the different contrast of some layers is the optical image, and from the optical image, this is the monolayer having this one is the more faint or more transparent one. This is the monolayer. So they could see that this is the monolayer, and then they have confirmed this monolayer by some other techniques, by the Raman spectroscopy and atomic force microscopy also. So the optical imaging is one of the technique to find out that what is the number of layers, but most convincing one is through the Raman spectra. So depending on the number of layers, as you can see it from here, the features of the Raman spectra are different. Here is this one is known as the G band, and here is the 2D band. As you can see, for the single layer case, this 2D band is more symmetric and narrower, whereas the G band, this one, has a much lower intensity as compared to the 2D band. However, if you keep on increasing the layer numbers, you can see that the intensity of this 2D band decreases as compared to this one, and as well as becomes broadened. Now the question is, what are the sources of this G band and the 2D band? So source of this G band and 2D band, this particular G band appears due to the
Not audible, sir.
as you can see from what is happening. So as you can see it from here, that these carbons, they are arranged in a hexagonal manner, and the in-plane stretching of these carbons, they gives rise to the G band, which is appears over here. And this 2D band is appears due to the inter-valley transition as shown here. So this particular electronic structure I am going to discuss later on. So, but as you can see from here that this here, I'm not sure that whether this is very much clear to you or not. So the G band appears due to the within the valence band to conduction band. If you shine a laser, the electron will jump from the valence band to the conduction band, and then it can lose certain energy due to the due to the vibration, and then it can come over here. So from this, you can get the optical transition, you can get the information of the vibrational transition, because what you generally take for the Raman, that is this is the optical one, but this kind of vibrational energy, you are not using the laser beam with a energy very similar to these vibrational energies. You are actually exciting the electrons from valence band to the conduction band, and there is it loses some energy due to the collision with the phonon, and it comes back over here, so that from here you can get the information of the vibrational spectrum. So this kind of transition, this is the G transition, which appears due to the stretching mode vibrations, and it can have some inter-valley transitions, like it excited from here to here due to the optical excitation. Then it jumped to the another valley. Those who are familiar with the different valleys, they can get it. But if not, I shall come back to here again to show that what are the meanings of the different valleys. Okay, it can go to the different valley and then come back to here, and this is the D band, and it can have some going over there, then come to here, then here to here. So these kind of transitions, these are there, and it is obvious from this G, D, and different G prime bands are also there, as you can see in this case. So D is there, 2D is there, G is there, and there are G primes also. And if the graphene, you wrap up it, there are some analogs which are already known much before the graphene. These are the carbon nanotubes, and this is buckyball. So these are the analogs which already discovered much before the graphene. These are the wrap form, but the two-dimensional freestanding form discovered much later. Yeah. Hello? Yeah. So now the graphene is not alone in this category. I have pointed out here, I have some of these other two-dimensional materials. So like the hexagonal boron nitride, HBN, as you can see that its structure looks like very similar to the hexagon of the graphene. However, these atoms which I have shown here, shown in a different color, that means these atoms are the boron and the other atoms, these are the nitrogen. So although the structure looks like similar to the graphene, however, here the compositions are different. Here all atoms are not of the same type, but there are two different types of atoms are there. But their properties, this is again a two-dimensional materials, and it shows the completely different properties as compared to the graphene. Here I have shown the molybdenum disulfide, MOS2, and from the top view, you can see that these are the sulfur and these are the molybdenum. It again sees like a two-dimensional structure, But however, if you see from this is the top view, from the top view, it seems like that they are all in the plane. However, in the side view, you can see that they are not in the same plane. So these are the planar structure, but this one is not a planar structure. Although from the top view, it looks like a hexagon and very similar to the graphene and hexagonal structure, only composition is different. However, they have some difference as compared to the graphene, that although those atoms occupy the hexagonal positions, but they are at the different heights. This is another example of silicon, which is also very similar to the graphene. Here, all the atoms are of silicon. So this is known as this is derived from silicon. That's why the name is silicon. And this one is known as, this is the stannine. Okay, this is the from the tin materials. So there are other derivatives also. For example, here, this is known as the graphene. This is basically the graphene. However, all the carbon atoms at the different points, they are saturated with the hydrogens on the both sides. So its name, it has a different name, is known as the graphene. And people use also the graphene oxide. This particular one is derived from the graphite, but not by the scotch taping method, which I showed earlier. This is basically using some chemical reaction to separate out the layers of graphene from the graphite. But during the process of the chemical treatment, this hexagonal structure throughout the graphene sheet not maintained. There are different functional groups attached over there, and there are some other topological defects like the pentagon and hexagon also introduced within this system. So graphene oxide. And another one is the recently discovered is the molybdenum carbide. It's this kind of two-dimensional material. This is also known as the magazines. So this is some little bit of different one, because in this case the parent material here, this is known as the max phase. It's not like a layered material which I showed for the graphene, that the different layers connected by the van der Waals interaction. Here, these are the different layers of the molybdenum carbide or the titanium carbides. So they are connected by some aluminum layer in between. So the parent material is not a layered material at all. But however, people have the Gogotsi group, they have actually etched out this interlayer aluminum from there. If they etch out the interlayer aluminum, ultimately it looks like a very similar to the graphite kind of things, where there are different layers, they are connected by the van der Waals interaction and they are separated to each other. These are known as the magazine. It is a new class of materials recently discovered. I have just mentioned about the molybdenum carbide, but there are a huge range of materials, titanium carbide, Ti3C2, TiC, and the molybdenum based one. So, I mean, all sorts of materials right now coming in the form of this kind of magazine, because it is derived from the three-dimensional materials, and a lot of opportunity that are there in the case of these magazines, and they show very different properties depending on the composition. Now comes to the properties of the graphene. So the graphene is very, very strong. It is 300 times stronger than the steel. However, I mean, this particular example also gives some wrong impression that if you have a single layer of this example is being used very frequently. However, you need to consider that if you take really a single layer of graphene and put some kind of elephant or put some pressure, it can tear up easily. The thing is that the meaning of this 300 times stronger than the steel, it is the normalized one. If you take the similar thickness of the steel, then the strength of this graphene will be 300 times higher. I mean, you should not compare some atomic layers of graphene with the very thick steel. So you have to compare with the similar thickness. I mean, normalized with the thickness. And the mobility is very, very high. It's the transport is like a ballistic transport. The electrons can move within the graphene without much of scattering over here. So it shows a very high mobility. Again, there is a caution here. This kind of mobility is for obtained with the freestanding one. But if you put the graphene on any substrate, there will be a charge trap in between the graphene and the substrate. They can make the electrons localized around. ultimately the mobility reduces a lot. In most of the practical applications, it remains between 1,000 to 5,000 only. It's not like that. So to get the, I mean, there is a lot of challenges are there. So people are working on it to get its intrinsic mobility, so that people can design some electronic devices with faster and faster. And another most important thing is that it has an ultra high surface area. Again, it's a normalized with its mass. If you consider 1 gram of graphene, it has a surface area of 2,630 meters square. To get a sense of the surface area, actually with the less than 1 gram of graphene, you can cover the entire football ground. So that means with a very tiny amount of graphene, you can use it for different applications where surface area matters. Now, I would like to give some kind of theoretical aspects of this electronic structure of graphene. So, as I showed earlier, this is the structure of the graphene, which contains all of them are carbon atoms. However, in this case, I have shown with the 2 different colors. So, I have shown with the 2 different colors because of the fact that this particular graphene is not a Bravais lattice. Bravais lattice means that if you consider this carbon and this a single color, they are all periodic. If you go in the same period, they will repeat it itself. But however, this one and this one, they are not periodic. Okay, so if you go this way, they are not periodic. So that means this set of carbons, they consist of one lattice. It is called the sublattice of graphene, and another color. They are also periodic. So it seems like the 2 different periodic structure, they interpenetrate each other. So these 2 different lattices are known as the sublattices of graphene. So that's why they are shown here with the 2 different colors. And in this case, I have shown like A1 and A2. These are the Bravais lattice vector of this particular sublattice, this A1 and A2. And at this site, if you consider this is the lattice site, then this atom and this atom constitute a basis, because you know that a crystal is nothing but a lattice point, and every lattice point, if you put a basis, you will get the entire crystal. So this is a triangular lattice. This is a triangle, and each and every lattice point, if you put these 2 atoms, every point, you will get the entire structure. You can see it from here. Like this one, you put this structure, exactly the same thing you put here, exactly the same thing you put here. You will get entire structure. So here, so the thing is that, so this is a 2 atom basis and it's a triangular lattice. And if you just calculate from the triangular lattice, what is the lattice in the reciprocal space, that is in the K space, because we generally represent the electronic structure in the K space. If you do it for a triangular lattice, if you will get a hexagonal Brillouin zone. This is the first Brillouin zone, which looks like a hexagon over here. And in this zone, you see there are 6 corners. These are the Brillouin zones, and these are 6 corners. However, this point and this point and this point, if you consider a triangle connecting the 3 points, they are all equivalent points. What is the meaning of the equivalent point is that this point and this point, you can go from this point to this point just by using a reciprocal lattice vector like B1. So if you can go from one lattice point to the another lattice point by using a reciprocal lattice vector, those points are equivalent points. Okay, so whatever will be the behavior of electron at this point, the behavior will be exactly similar at this point because they are equivalent point. However, if we consider this K point and this K prime point, they are not connected by any of this reciprocal lattice. So these 2 points, K and K prime, they are non-equivalent points. So in the Brillouin zone, there are 6 corner points. This point is a K point, this point is a K point, this point is a K point. That means these 3 points are equivalent. And this is K prime, this is K prime, and this is K prime. So there are 2 sets of non-equivalent points, that is a K and K prime. And if I check what is the electronic structure at the different K points, it looks like this one. So as you can see that at each and every K points, This is the lower one is the valence band and the upper one is the conduction band. And around this K point, it looks like this kind of conics, they actually touch each other. So this touching point is known as the Fermi level here. They touches each other. So conduction and valence band touches each other at these 2 points. However, it is not a metal. In the case of metal, there is an overlap of the conduction and the valence band. In this case, although the valence band and conduction band touches each other, exactly at the point where they touch each other, there is a density of states. That means how many chairs are there for the electron to sit. That is nothing but the density of states. That is 0 exactly over here. So at this point, there is no density of states at the Fermi level, but it increases if you go up or if you go down. So density of states increases, but at the point density of states is 0, and this point is known as the Dirac point. These points. So now you can see that here in the case of graphene, there are 2 sets of K and K prime points, 6 Dirac points, but out of them K and K prime, they are non-equivalent points. So here there is some interesting fact is that the dispersion relationship is linear. That means energy is related to the momentum with a linear relationship, because you see it's a kind of linear relationship here. If you K increases, the energy increases linearly. But most of the cases we know from for classical materials, they follow the quadratic in nature, the p square by 2m form. But this linear relationship is much different than what we know from some basic physics, that is generally follow the quadratic relationship. And the important thing, another term is that the Valley degeneracy is that suppose an electron is there at K point and electron is there at K prime point. You see their behavior, energy versus momentum behavior, exactly similar. However, because these 2 electrons are not equivalent, so that means the electron over here and electron over here, K prime, K and K prime, we can distinguish them by their Valley index. So one electron here, we can consider it belongs to the K prime Valley, and another electron, it belongs to the K Valley. It is similar to the like a spin up and spin down state. It has 2 different states. Here is it's like a spin states, like a pseudo spin. Here this is the Valley index, and this one is the different Valley index. So using this concept, people are also right now trying to design some electronics, is known as the Vallectronics, where they are taking into consideration of these particular features. And importantly, as I mentioned, that what is the consequence? There is a consequence of this linear dispersion relationship. When we consider the effective mass of electrons, the effective mass means electron. You know that the electron has a mass. Real mass of electron is 9.1 × 10 to the minus 31 kg. That is the mass of electrons. However, the effective mass means if the same electron is put within a crystal, and then due to the interaction with the crystal, its effective mass will be different. It's like when something floats in a water. So when you push the same thing in the water, its mass looks different than its original mass. That is the effective mass. So effective mass we get from this. If we know the relationship, the energy momentum relationship, we can get the effective mass by just making the relationship. Take the double derivative of the energy versus K relationship and take the inverse of it like this. However, if you take the same relation, apply the same here, you see that you will get 0. So this is h cross square by 0. So it's an undefined quantity. You cannot define like some effective mass of electron in this case. Practically, this is actually the electron behaves like a massless particle here. Please consider it's the effective one. It's not the real mass of electrons. So it behaves like within a graphene, it behaves like a massless particles, and it follows the relativistic relationship. And if m is 0, massless particles, it follows the E proportional to P momentum, which is the case also here, E proportional to this H cross K. And there are, because of this particular behavior, this conical behavior, a lot of possibilities are there to tune the electronic properties of the graphene. For example, you can doping by gating, is there, I think, let us say. And here I'm going to discuss about the electron transfer doping from external species. Suppose on the graphene, if you coat some molecules, now here is the homo level and there's LUMO level of these organic molecules. And if there this here there are some in the LUMO levels, there are certain vacant states, and it is there at the below the Dirac point, then there will be some transfer of electron from here. So in this case, if there is a transfer of electron from the valence band to this case, there will be lots of vacancy in the valence band. So it will turn into a p-type material. Similarly, in this case, if the HOMO level is higher than the Dirac point, there can have a shift of the electrons from here to here. Ultimately, it will dope with the n-type because these electrons will take in the conduction band. And there are also possibilities of tuning these electronic properties of the graphene by heteroatom doping, because it is a surface only material. There is only a surface. If anything you do on the surface, immediately it will affect on his electronic properties. For example, even if suppose you put something, you touch with your hand, immediately its electronic properties will also going to change, because this is only surface, there is no bulk. And people are trying to control the electronic properties of the graphene by making some different heteroatom doping, replacing the carbon sites with the nitrogens, and nitrogen can be doped at the different point. If it is here connected with the 3 different carbon, this is known as the graphitic or quaternary nitrogen, and it can be here, this is like this, it can be pyridinic and can be connected with the 5-member ring, it can be the pyrolytic, and all those processes can tune their electronic properties. And if you are interested to check that how the doping can change the electronic properties, you can follow this review article which we wrote long back. And here, I mean, going beyond the graphene, let me discuss about something about the molybdenum disulfide. And molybdenum disulfide, as I have shown here, and you can see if I just look back, that what are the differences here? Of course, one difference is that it looks like a hexagon, but there is some difference here. The basis, there's one is molybdenum and one is sulfide. Due to this, there is a asymmetry in the sublattices. This is one sublattice and this is another sublattice. These two sublattices are not same. As a result, it shows some band gap. In the case of graphene, there is no band gap, but here there is a band gap. And importantly, for the case of the bulk molybdenum sulfide, which is there in the nature, over there, this particular material is a indirect band gap materials, because you can see that this lower of the conduction band and top of the valence band, they are not at the same K value. They are at a different K value, which I have shown in this kind of arrow. So this is the indirect band gap materials in a bulk. However, whenever you go from the bulk to the single layer, so in this case, you see that right now the bottom of this conduction band and the top of the valence band, they are at the same K value. So this is the direct band gap. So going from the bulk to the monolayer, so MOS2 turns from the bulk to the from the indirect band gap to the direct band gap materials. And this particular happens because of the loss of some interseed interaction, because if you put another layer on the top of it, there will be interaction between this layer and the top layer, that is this antibonding of PZ orbital. So this particular one, this top one is basically arises due to the antibonding of D of molybdenum and PZ of the S. Whenever there is a less interaction between these two layers, the top layers, and when this one actually goes down and down, ultimately this point becomes the band gap. And MOS2, this one I have shown at this particular one at some particular, this is the K value. But however, if we see that at all the different K values, at the K and the minus K means these are the K prime values, it's look little bit different than the graphene. Here you see that although there are some exactly the 6 corners are there, however, you see that in this case the valence band, they actually separated to each other. So the degeneracy in the valence band removed, and due to the strong spin orbit interaction over here. And of course, and another important thing is between the k and the minus k, means this is equivalent to k prime point. You see that although there is a the degeneracy between the two spins removed, you see here that this down spin is up, this band is up, then the up spin band is here. But in the case, it is just the reverse in this case. So this is an interesting feature which people are using to for the electronics things here. And now I shall go to the how to synthesize the two-dimensional materials. As I just mentioned, the mechanical cleavage by just cross-stepping, which is the first method to separate the graphene. But for large scale or practical usage, this is never been used. The large scale case, it's a solvent sonication. You can take some two-dimensional materials within a solvent and use the strong sonication. During the sonication, the bubbles generated by this sonication, they actually hit the edges and separate these layers one by one. This is a solvent sonication. Similarly, you can have a vapor phase bottom-up growth, in which you use a substrate and then pass some vapor of these materials, like suppose MOS2, and it deposited over this substrate. This is the vapor phase method. And for the graphene, they use generally some copper foil and pass some carbon containing species like a methane, and this methane interact with the copper and the carbon dissolve with the copper, but during the cooling down, so they carbon precipitated in the form of graphene over it, which can be, this graphene can be separated from the copper foil. And about the applications of graphene, this is the one of the application, this is the field effect transistor, which is very similar to some IV characterization. Like this one, this is the graphene put over the SiO2 layer, and here is one electrode and another electrode. So if you pass suppose you just apply a voltage, you will get a current, just the IV characteristics over here. However, if you connect a different voltage, so this is a backgate voltage with the drain, or you connect with the source, then what can happen? This is a capacitive effect will happen, because you see that backgate one is a metal and there is an insulator and then there is a graphene. So it looks like a simple capacitor, which we studied from our school days, that there are two different plates separated by a insulating layer. So in this case, if you apply any voltage, some of the electrons can go from these bagged electrodes to the graphene, so that the conductivity of the graphene will change. With the application of the same voltage, now you will get a larger current. Similarly, if you apply the different voltage, if you apply the positive voltage, so some of the electrons will go from the graphene to this electrode, so that you can actually reduce the number of electrons from here, so that the IV characteristics of the graphene you can change by this gating. This is nothing but the field effect transistor of graphene. So normal, like a normal capacitor, which I have shown here. If you use the no gate voltage, this valence band is completely filled and the conduction band is completely empty. But if you use the this one in this direction, V is not negative, so some of the electrons will go to the gate, so that this valence band become empty. So right now these electrons can take part in the conduction, because you know that a completely filled band is an inert band. It cannot contribute to the conduction unless or until you make vacant any of the band. And here is the one interesting fact, is that with the quantum capacitance, which never encountered in the three-dimensional materials, it is the very important properties of the two-dimensional electron gas. So this is some interesting property of this graphene, that is the quantum capacitance, which people never seen in the other three-dimensional materials. This is the property of the two-dimensional electron gas. So here what happens, you see that, I can explain from this side. This is schematic. Suppose, some analogy from here. Suppose this is a glass filled with the water, and this is a glass, another it's filled with the water. Now, if you take some amount of water and put it here, if the diameter of this glass is high, you cannot see any change of the water level, because it's putting, if you take the one bucket of water and put it in the sea, in the ocean, you cannot see the change of the water level in the ocean level like that. But however, if you take some water from here and put it here, in this case, because it is so narrow, So there will be a change in the water level also here. Okay, so this is the thing for the graphene. So suppose in this case this is a metal and this is a graphene. Now if you transfer the some electrons from metal to graphene, there will be a change in the level of the electrons here, because the density of states, that means the number of chairs it can accommodate, these are the very low. So if you put some electrons from this side to this side, then there will be immediate change in the level of the electrons. Okay, so as a result, what happens? So this is the some analogy over here. Like if you have some materials which have a very large density of states around this point, so even if you transfer some electrons from one side to the another side, ultimately we can consider the change in the level. It's very much, I mean, irrelevant. It's negligibly small because the density of states is huge. But case of the graphene, because density of states is low, there will be a change in the level of the electrons. As a result, as you can see from here, that if you put the different voltage, one is going up and one is going down, and the difference of these two levels is nothing but E into V. Because if you apply the voltage V, so the change in the energy difference from here, that is the Q into V, it is here. But in this case, you see the difference in the level, it is not in Q into V, but there is some additional change because of the change of this level of the electrons. So this change actually gives rise to the another capacitance. This change of energy can be accounted in terms of the capacitance. This is known as the quantum capacitance, because this is entirely the quantum in nature, because this never happens. This is actually appearing due to the, I mean, very low density of states around the Fermi level. And these two capacitance, like this one, like epsilon into epsilon 0 by d, this one we know as the capacitance of a 2D some capacitor, but together with that there is an additional one term. So this contains that this is the DEF by this is the DNS. So this is the number of electrons, and if the density of electrons around the Fermi level changes a lot, then there will be this value will be larger. In the case of graphene, because of the low density of states, little bit of change of n, there is a large change in here, this particular one. So it gives a significant quantum capacitance, which you have to take into account for designing a field effect transistors. And this is one example of the Dirac point tuning by complementary doping. As I mentioned that if you use, this is one graphene is taken, and then one side of the graphene you coat with some polymer, another side you coat with a different polymer. We are not doing anything but just coating two polymers. Because of the transfer of the electrons from HOMO to LUMO or LUMO to HOMO, depending on their position with respect to the Dirac point, we can make this one P type or N type. Ultimately, you can make a PN junction. It's an in-plane PN junction by making the molecular, this is known as the molecular doping. And the graphene is also used extensively for the optoelectronic case, because you see that this is the intrinsic graphene. So if you excite the light with the different frequencies, the electron can excite from it because there is no band gap. So all of these frequencies it can absorb. So that's why it has a broadband absorption. However, if you want to tune it absorption, what you can do, you can dope with some N type. Suppose you dope with N type, that means up to certain level it is filled, so that the electrons from here it cannot jump to here. Only the electrons from here it can jump above the levels which are already filled. So you have a selectivity that which wavelengths you would like to absorb by making is the N type or the P type doping. And because of this large surface area, you can use it for the energy storage also. In the case of energy storage, these are the graphene layers, and on the graphene layers, some ions just sit on the top of the graphene layers, and how many ions you can store, it will gives rise to the much of your energy storage. So because of the surface area and each and the individual ions, they can sit over the graphene. So by this process, you can get with some small amount of graphene, you can store a lot of, very, very huge energies. But here, there is a challenge. The challenge is these graphenes they try to restack each other because they have a strong interaction. Even if you separate them, again, when you want to use in bulk scale, a lot of graphenes are there. I mean, very close, close separation. They can stack to each other. Ultimately, you will lose the surface area in between the two graphene sheets. So to get the surface area, so it is possible to implement some concept of a hydrogel where the graphene sheets, these are the sheets, they are separated by the water molecules. So here is a large sheet. You can get some large hydrogel kind of things where the graphene sheets, the tiny graphene sheets, micron size graphene sheets, they are integrated over the long range, and there is some water molecule trapped in between. So this particular structure can give rise to the very high energy density, and also possible to have some defect engineering. For example, here we also showed earlier that we made some porous graphene, made some pores over here, and then we wanted to introduce some big, large, some dopant like a sulfur and phosphorus, because introducing these large atom within this structure is very difficult because they have a larger size. It is hard to put within this framework. But if you can make some pore over here, these larger atoms can be arranged around these points and you will get the doped materials.